Now let's take a look at a real example of a system architecture DSM model. Here we'll look at the system architecture of the Pratt & Whitney 4098 jet engine. This is a commercial jet engine that goes on Boeing and other airplanes. The engine itself is decomposed into 8 subsystems and then further into 54 major components. And we'll be able to see those 2 levels of decomposition in this system architecture DSM model. The 8 subsystems, starting from front of the engine, include the fan, the low-pressure compressor, the high-pressure compressor, combustion chamber, high-pressure turbine, low-pressure turbine, and then 2 more subsystems that are pretty distributed connecting throughout the whole engine, and those are mechanical components and externals and controls. In the matrix itself, what you see is the 8 subsystems listed from top to bottom, fan, LPC, HPC, and so forth. And each of these subsystems is decomposed into its primary components. So the fan, for example, is decomposed into several, low-pressure compressor into several more. And what we have in the matrix is the network of interfaces between those components. So the fan being represented by the first few components, you see a black square representing the fan. The interfaces inside that black square, those red marks, represent the interfaces between the fan's components. Now the red marks are of 2 different shades. Those represented what we thought of as the high-strength interfaces and the low-strength interfaces. And in particular, when we captured these interfaces, we very carefully documented 5 different types of interfaces, those being spatial connections, structural connections, energy flows, materials flows, data and controls. You'll notice that some of the subsystems have a lot of interfaces inside and very few across. I think of these as modular subsystems. Look at the high-pressure turbine, for example, the 5th subsystem down. The square representing the high-pressure turbine is full. That is, every component inside HPT interfaces with each of the other components. On the other hand, it has fairly few interactions across, that is, to other components in other subsystems. And that's true of all the modular subsystems. The distributed subsystems, mechanical components, externals, and controls, well, those subsystems are made up of components that have a lot of interfaces across. Their nature is very connective, and yet they have less to do with each other. And so I think of these as the more distributed subsystems. So what we have in the DSM is an overall view of the system architecture. How is it decomposed into subsystems and then further into components? 2 levels of decomposition in this case. And we can ask questions such as, do we like the system architecture? Can we change it or improve it? Now that you've seen a system architecture DSM model, I'd like to show you exactly how we go about creating one. Here we'll look at the example of an automobile climate control system. So this is what creates heating and cooling for passengers in an automobile. And what you have here is a diagram representing the different components in this system, and you can see a little bit of how they relate to each other. The question that we'll ask here is, how should we organize the development of these different components? Are there natural subsystems or systems that we would decompose this into? What is the sensible system architecture? One option that we have is to organize it in 2 chunks. Which are the components inside the vehicle interior? Which are the components that are under the hood of the vehicle? A second option that we have is to think of the different fluid flows. So there's the flow of fluids through the air conditioning system, another loop through the heating system, and there's even some flow of air at the front end of the vehicle. So the way we'll do this, of course, is with the design structure matrix. So we'll lay out the DSM by listing the components as the rows of the matrix, and those components are also represented, of course, in the columns. We'll then need to fill in the interactions. We need to identify each of the interfaces between these components. And finally, we'll attempt to cluster it in order to reveal the system architecture. Now, we'll do this matrix analysis in Microsoft Excel. I've got a spreadsheet, which I'll give you, that has a macro that helps us to manipulate the matrix manually. We'll start by identifying the interfaces between the components and representing those interfaces using marks in the matrix. I could start, for example, with the evaporator case, the first row, and I would ask, with which other components does the evaporator case have interfaces? Well, the evaporator case encloses the heater core, evaporator, blower controls, and the motor. So I would put marks in the matrix representing those interfaces, these 4 marks. Now, since this is a system architecture matrix, if one component interfaces with another, then we also have vice versa in most cases. So I would put a symmetric set of marks like that. So here are the first 4 interfaces. I would think through all the components, all the interfaces, and fill in marks in the matrix in that fashion. When you do that, we'd have a full set of marks, and here's what those would look like. So these are the set of interfaces that I believe are in this system. And now we'd like to identify what is the sensible system architecture. And what I'll do is I'll show you how would we cluster or experiment with different possible clusterings. So I'll show you, for example, one sensible clustering. I would think one sensible clustering is the one that represented those fluid flows. Well, there's a set of components in the heater system. There's a set of components in the air conditioning system. And actually the third set of flows would perhaps be the interior air. And so what we can do is we'll fill into this first column a code representing those different subsystems. So the evaporator, we'll use a code of E. So the evaporator, I'll put E for the case, the heater core, the evaporator, the controls, and the motor. The accumulator, compressor, those are part of the air conditioning subsystem, so I'll use the code of A for air conditioning. The fan and radiator, those are part of the heating system, so I'll use a code of H. Condenser's part of the air conditioning. The engine provides the heat for the heating system. The heater hose is part of the heating. Air conditioning hose is part of air conditioning. So let's see, what does that system architecture look like? What I'll do is I'll hit the sort button, and this will run the macro that sorts the matrix, sorts the rows and columns according to the alphabetical order of that key in the first column. I hit the sort button, and you see what it's done is it's put all these components representing the air conditioning system up here. So that's these. That looks like a sensible cluster. This is the evaporator subsystem, or the evaporator case. This is the heating subsystem. The trouble is there are some components that are really part of 2. For example, the evaporator case, this is part of the air conditioning subsystem and the heating subsystem. So I'd really like that one naturally to be in both. So maybe I'll give it the code of AE. It's really already sorted there. And in a similar way, well, the heater core, it's part of the evaporator subsystem. It's really also part of the heating subsystem. So maybe I want to put that next to the heating system. So I give that a code of EH. And you'll see how that changes this a little bit slightly. Now you see we have a set of interactions for each of these 3 subsystems. What this might look like when we've shaded it, made it look a little bit neater, is this. Here we have the air conditioning subsystem. It overlaps a bit with the blower subsystem or the evaporator subsystem. We have the heating subsystem, which overlaps again with the blower and evaporator case subsystem. There are a few interfaces that are outside this clustering, that is outside of any one subsystem, that tie them together, and those are represented by these stray marks in the corners of the matrix.